right, welcome to Unit 3. Unit 3 is all about trigonometric and polar functions, which are two types of functions you've probably not studied very much in any class. Your probably only exposure to trigonometric functions is SOHCAHTOA. You might have learned that in geometry class. Sine, cosine, and tangent. We're going to bring all of that into this unit, but first we're going to just talk about what these types of functions represent in real life. And those sorts of things are called periodic phenomena. A periodic relationship between two variables occurs when the output values demonstrate a repeating pattern over successive equal length intervals. So those of you in physics, if you've done anything with springs, you know when you drop a weight on a spring, the spring goes down and up and down and up and down and up, and gravity aside and friction aside, it would keep doing that shape over and over and over again across its entire domain. Those of you in health sciences, if you look at an EKG, the heart monitor goes boop, 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 over and over again, unless you're in cardiac arrest, right? But those shapes that repeat themselves over and over again are periodic phenomenon, okay? The important idea for today is we're looking at the period of a periodic function. The period of a periodic function is the length of the input variables, not output variables, input variables that it takes for the function to complete one cycle. Ignore my typo, please. The period of a periodic function is the length of the input values that it takes for the function to complete one cycle. So we want whatever shape on our graph that we see to repeat. So we're going to be looking at repeating patterns and need to basically cut out one piece of the repeating pattern so that we can look at it. Wherever you want to start that shape is fine. So we'll start where it's very easiest on this first example. And if we look, we have this first shape that goes up, over, and down. Do you see how that blue shape would then repeat itself? Diagonal, across, and down. Diagonal, across, and down if we kept repeating this shape. That means that that one shape that I've highlighted in blue is one period of this function, one cycle of the function. This function has a period of 4 because it takes 4 units, 1, 2, 3, 4, for that shape to start repeating again. So our goal today is to really nail down the idea of a cycle or a period of this function. So if we wanted to continue to draw 2 additional periods for the graph of f on these axes above, all we're going to do is take our pencil and repeat that shape 2 more times. So from 7 to 9, I'm going to go across. From 9 to 10, I'm going to go flat. And from 10 to 11, I'm going to quickly go down. That repeats the shape. I've drawn one more period of this function. Then we can go diagonal up from 11 to 13, flat from 13 to 14, and quickly diagonal down from 14 to 15. We have repeated the shape. We've drawn 2 more periods of the function. So now our job is to identify what the period of a graph would be. So this one, it doesn't tell you what the period is. Example 2 wants you to find the period. So take a second and look at that shape. Find a place where the shape starts to repeat, and then I want you to count from beginning to end how long it takes for that shape to repeat one cycle. Again, it doesn't really matter where you start to look. My brain wanted to start looking at 0 instead of where the graph actually starts, so I'm going to start looking here. This graph goes down, then it goes up, then it goes across. Right after that checkmark looking shape, it would go down again and start repeating, yes? How long did it take for me to go from start to finish of the shape? Good morning. 5, which means that the period of this function is 5. That is the least possible value of the period. I believe in physics, and this is me trying to remember from when I took physics back in the old days, you use the capital T for period. In physics, we're not using that symbol in this class, so you'll just write the word period equals or period is 5. But if you know that for yourself, you can use that. Now, because this shape repeats itself over and over again, we can use the idea of repeating shapes to find or evaluate the function anywhere on its domain. Because right here, we only have information from -2 to 9 on this graph. So we would have to extrapolate some data to figure out where g of 14 is, because 14 is not an input value I can see. But since we know that this shape repeats itself every 5 units, we can do the following. Instead of writing g of 14, I'm going to rewrite 14 as some multiple of 5 and a remainder, meaning how can you multiply the number 5 to get close to 14? 5 times what? 5 times 2 is how much left over? 4. So 5 times 2 plus 4 is 14. Every 5 units, this graph resets. So really, g of 14 is exactly like the output at g of 4, that remainder number. G of 4 is something I can read off the graph. What is the output when x is equal to 4? What's the output when x is equal to 4? 7. So g of 14 is 7 because g of 4 is 7. And those would be at the same point on this repeating shape on each cycle. Now what if we do this for 72? Oh yeah, and let's get our brains pumping. 5 times what gets you close to 72? 14. 5 times 14 is 70, which means how many left over do I have? 2. So g of 72 is the same as g of 2. And if we read our graph, what is g of 2? 6. So g of 72 is just like g of 2, which is 6. Because I'm just using that repeating idea of this 5-unit long cycle to get down to a number I do know. Ooh, but what if we go to negative numbers? We're going to do this problem in 2 ways because I think there's 2 ways to look at it. Let's use the number negative 5 just for right now. If I had negative 5 and I want to get close to negative 17, what could I multiply it by? Times 3. That would be negative 15. So what do I have to add to this to get to negative 17? A negative 2, or like minus 2. I know those are the same things, yeah. Okay, so that means since any repeat of 5 gives you the same shape, this is going to be the same as g of negative 2. Based on what you can see on the graph, can you read g of negative 2? What is g of negative 2? 7. Let's do this a different way because some of us don't like using negative numbers, and that's okay. Or subtracting, I guess. If we did negative 5 times 4, what's negative 5 times 4? How could I get to negative 17 from negative 20? Plus 3. So g of negative 17 is just like g of negative 2, which is just like g of 3. What's g of 3? 7. Any multiple of 5 with the same remainder is going to give you the same output value because this cycle is going to repeat every single time. Make sense? Okay. So similarly, I can ask you the same kind of question but give you a table. In this table, it does give you the period. It says the graph of h is periodic, good morning, with a period of 5. So that means we know, just like the example above, this one repeats every 5 units. It's not always going to be 5. We just picked 2 examples with 5. The values of h are shown at selected values. Find the following values, and we want to know h of negative 2. Is negative 2 a number that I know for x values on this table? No, so I have to do a little bit of work to make this happen. Because these numbers are all pretty close together, and it's not like 72, instead of working like we did in the top problem, which you can do, I want you to just add and subtract the number 5. If you add the number 5 to negative 2, what do you get? 3. So h of negative 2 and h of 3 should be the same output value because they're 5 units apart from each other. And what is h of 3? 0. So h of negative 2 is also 0 because those are 5 units apart from each other. Is h of 6 something in my table? No, but can we add or subtract the number 5 to get something from my table? Yeah, would I add or subtract 5? Subtract, because 6 minus 5 is 1, and h of 1 is negative 2, which means h of 6 is also negative 2. Ooh, letter C, what am I asking you to do when I say h of negative 9? Yeah, you have to do this process twice. Very good. Do we start on the outside or on the inside? Inside, very good. So h of 9. 9 is not something from my table, but can I add or subtract 5 to find something from my table? Yeah, so h of 9 is like h of 4, right? And h of 4 is 3. Is 3 something I know from my table? Yeah, so I don't need to add or subtract 5. What is h of 3? 0. So h of 9 is 0, because h of 4, which is h of 3, is 0. So any multiple of 5 is going to basically reset the cycle. And so you can always just take the extra remainder number and evaluate there. For part D, it says evaluate h of 5k minus 3, where k is an integer. Now this looks crazy, but this number 5 that's multiplied by my integer k, isn't that the period length? Which means my remainder, when I'm doing that multiplication, is just negative 3. So I'm really evaluating h of negative 3 repeated all over this graph, or every integer we multiply by k. Integer is a number with no decimal, no fraction, for lack of better words today. H of negative 3, is that on my table? No, but can I add or subtract 5, maybe multiple times, to find something from my table? Yeah, h of 3, negative 3, if I add 5, that gets me to 2. That's not in my table. If I add 5, it gets me to 7. Oh, snap, that's in my table. What is h of 7? 2. So anytime you are multiplying by your period length, it's like the cycle is restarting. So you can go back to the beginning of that cycle and just use that one cycle or one table to answer your questions. Now that being said, and really from this example, we kind of see it. A periodic function starts with a basic pattern and translate that pattern repeatedly over its domain. So we have the check mark shape, and we move it over, and then we would move it over, and we'd move it over and over again. So as a result, we consider a periodic function as a horizontal translation of itself. So it's taking itself and it's moving it, the period length, over and over again. So in example 4, the table, since the period of h was 5, we could translate the graph horizontally 5 units left or right and end up with the same graph, which means that the function h satisfies the following equations for all values of x. That h of x is equal to the same output value when you shift it 5 units left or right, in this case to the right. So we're just repeating that shape over and over again, which means with one cycle's information, we know the information for the entire domain of the function, because it will just repeat that over and over again at the length of your period. All right, on back we go. Example 5 says the graph of f is periodic with a domain of all real numbers, which means that this graph really should extend from negative infinity to positive infinity, but we only took a little chunk of it. We have 2 full periods shown on the graph. We want to find all input values that yield an output value of 1. So I want to know all of the solutions to the equation when the graph is equal to 1. Well, here's where the graph is equal to 1. Just visually based on the 2 periods that we see, what are the input values where this is equal to 1? But since we know that this repeats over and over again, where else is the graph going to be equal to 1? Ooh, how'd you get 10? Yeah, what's the period of this function? 4. So we know every 4 units, it's going to repeat the same values. So after 10, what would be the next time we have an output value of 1? And then, uh-oh. Is this ever going to stop? No, we could sit here for the rest of our life listing out the numbers. And we haven't even gone to the negative side because it repeats from negative infinity to infinity. So we need a better way to talk about what's called a general result or a general solution to one of these periodic functions. So the way we're going to do this, and this is the way I like to do it the most, is we're going to say x is equal to the very first one that you see. What's the first solution you see? 2, I agree. And then how long does it take? What is the period for you to get to the next one? So we're going to do 2 plus 4k given k is an integer. And I'm going to let you use mathematical shorthand for the phrase k is an integer. The way you write, everybody look up at the board so you can watch me write this because it's kind of funky. K is an element. It's like a little e, curvy e. And the integer symbol in mathematics is a bold Z. So the same way you wrote a bold R for all real numbers for your whole life, integers is a bold Z. This is how you would give a general solution to a periodic phenomenon. Because every 4 units after 2 or before 2, there is going to be a repeat of the pattern. And just so you remember what this means, k is an integer. That's what that means. Yes. Yes. Now our next example is actually a peek behind the curtain. There are 4 FRQs on your AP test, and they're very laid out for you, meaning I'm going to be able to show you when we get into AP review exactly what the FRQs are going to look like and how I want you to answer them, especially FRQ 3. We've technically already seen FRQ 1 and 2, by the way. We've been doing those last quarter. You just didn't know it. They didn't look exactly the same. But FRQ 3 is always going to look like this. Now, we're only doing 2 of the 3 parts, so 4 of the 6 points of this FRQ today. In a few lessons, we'll add in the next part. But example 6 is what FRQ 3 will look like. It says, the figure shows a large clock mounted to a vertical wall. The clock has an 8-inch long moving minute hand. The center of the clock is 120 inches directly above the floor. At time 0 minutes, the minute hand is pointed directly up to the 12. However, the clock is not working properly, and the minute hand is moving twice as fast as it should. Thus, the next time the minute hand points directly up to the 12 is at time 30 minutes. As the minute hand moves, the distance between the endpoint of the minute hand and the floor periodically decreases and increases. This is a great time for me to have a little side note for you. My clock that's above the TV right there obviously ran out of batteries over the break, and it is like bolted to the wall, so please don't look at that clock anymore. It's not the right time, and I can't get it off. I did get a ladder, so I'm going to try again today, but don't look at that clock today because it's also broken, like this example. The periodic function h models the distance in inches between the endpoint of the minute hand from the floor and the floor as a function of time in minutes. So let's pause right here and let's figure out what this figure is showing me. First things first, I want to know how high above the floor the center of the clock is. From the blurb, from the words, how high above the floor is the center of the clock? 120 inches. We got that information from right here. It is 120 inches directly above the floor. The piece of this puzzle that is moving is the minute hand. How long is the minute hand? 8-inch long moving hand. So that means that this distance, if we're looking here, is 8 inches. Fabulous. The 2 other pieces of information you need are a start and a stop time. It says that the minute hand at t equal to 0 is directly up at the top. When is the next time that that minute hand would go around the clock and end up back at the top? T equals 30. We know it should take 60 minutes, but this clock is broken, much like mine. Okay, our periodic function is going to model the distance between the end of the minute hand and the floor. So as this minute hand goes around the clock, is the distance between the end of the minute hand and the floor getting bigger or smaller? And then it goes back up. Is it getting bigger or smaller? Bigger. So it's going to go down and up and down and up. So the distance gets smaller, bigger, over and over again. That is a periodic phenomenon. Our goal in part A of FRQ3 is to give coordinate points that would represent one cycle of this periodic phenomenon. There's a lot of ways to deal with this. I think the easiest is always to think about the outputs first, which is interesting. So we're going to start with the outputs. We have a center line of this graph. What is the center line on your figure? 120, which means the outputs for both G and K are going to be at 120 because those dots are on the center line of your periodic phenomenon. It doesn't have any axes, so we can make the labels what we want. That's our goal. Now, when that minute hand is up at the top, how high above the floor is the minute hand? 128. How'd you get 128? You add 8 to 120, which means the output at F is 128. What's the output at P? Whoa, my voice cracked. P. The same thing, because it's the same height. Those should be the same height. Okay. What about J? What's the output on J? How'd you get 112? Very good. If that minute hand is facing down, it's 8 inches below the center line, which is 112. Congratulations, you got your first point on this FRQ. Getting the output correct is 1 point. Huzzah. Now we have to do the inputs. In this example, our input is time. Most of the time it's time. T equals time. Okay? The first time our minute hand is up at the top, what time is it? 0. So that means the input value, at F, where we're first time we're at the top, is 0. What's the input value or the time when we get back up to the top? 30. So P, the next time we're back up at the top, should be 30. Now this motion happens continuously, meaning it's not going to speed up or slow down like the left side of the clock goes faster than the right side of the clock. That's not a thing. So that means that we should right now be able to tell what time it is when this clock is at point J. What time do you think it would be? 15. How'd you get 15? Very good. Halfway between 0 and 30 is that lowest point, which means halfway between 0 and 30 is 15. Okay. Same idea. How do you think we get the G point? Halfway between 0 and 15. What's halfway between 0 and 15? 7.5. And then if we need K, K is halfway between 15 and 30. So what is the value for K? 22.5. Huzzah, you just got your second point on this FRQ. You get 2 points on FRQ3 for correctly giving me the inputs and the outputs of this function. Very good. The actual part B of FRQ3 we're not doing yet. So this next question is actually part C, and you've actually seen it before. I've been asking you this question since topic 1.1. It says refer to the graph of H in part A. We just filled in those coordinate points. Correct. Hooray. The T coordinate of G is T1, and the T coordinate of J is T2, which means we are looking at this portion of the graph. On the interval from T1 to T2, from G to J, which of the following is true about the function H? We're talking about the outputs. I would write that down. This is talking about the outputs. Maybe with a bunch of exclamation points. When it's talking about H, it's talking about the function itself, the outputs. Are those output values between G and J, are they positive or negative numbers? Positive. So we're going to get rid of C and D. And are the values increasing or decreasing? Decreasing because we go from 120 to 112. That's decreasing. Part 2 says describe how the rate of change of H is changing. I want you to highlight the words. The rate of change of H is changing. It's asking not about the function itself, but about the rate of change of the function. When we're asking about the rate of change of a function, what have I had you look at with a graph when I'm asking you to describe rate of change? Very good, yes, concavity. So we're just asking you about the concavity of this graph. At that point from G to J, is it concave up or concave down? Concave up, which means is my rate of change increasing or decreasing? Concave up? Increasing. Very good. So now we just have to formulate our sentence. And I know it's been a minute since you thought about this sentence, but the whole thing is in the question. Repeat the question. It says describe how the rate of change is changing. So you say the rate of change of H is increasing. Boom. Look, that was first half of the sentence because it gave it all to me. The rate of change is increasing because the graph of H is concave up on the interval from T1 to T2. Here are your two keywords that change every time. But the beginning of the sentence and the end of the sentence is straight up from the question. So you can always look at the question to remind yourself how to write the sentence. The one thing that I'm going to be extra super picky about, if you do not write that it's because the graph of H is concave up, if you use the word it, that's going to be wrong. Do not use the word it in your descriptions in this class. It's way too vague. Tell me what it means. Otherwise, I'm going to assume incorrectly. Don't use the word it. The rate of change of H is increasing because the graph of H is concave up on the interval from T1 to T2.